Okay, let's start. So today we're going to make a second group, and before I pass this paper around the class, I want to introduce what's going to be our next 5 project topics are. So I'm going to exclude the first 4 topics because that's the early part of our class. So here is our basically topic that I listed in the beginning of our semester. There are 9 topics, but I'm going to exclude the first 4. So the list starts from number 5, 5, 6, 7, 8, 9. And okay, so I explained about page flow until last lecture. And what you would like to produce is something like a heat map that I showed you last lecture. And that's one thing. And about the project 6, it's implementing your own neural network. So you probably have some group already presented their work. And I'm going to briefly explain the principle of neural network, and the objective is not just copy paste the outside library. You have to make your own or implement your own model into the Python code. So that you fully understand the theory behind any neural network. It doesn't have to be fancy or complicated, as long as you understand what you're doing. And oh, by the way, so if you chose these 2 topics for your first project, then you should choose another one. And the seventh one is the new one. It's about integration, and basically, I'll show you how it look like. It's basically about the Crofton's formula, which has a background in the multiple integral. And let's see. So basically, you're going to make a game. So this is the game I made. So I'm not asking you to make the same game. I'm showing you this as a prototype of the game that you're going to make. And you don't have to use the same gimmick that I show you here. But you should use some sort of the mathematical background related to the integration in your game. And this is one of the example how you can integrate the mathematical background in your game making. And what it does is, I think, so this white block is 2 by 1. So basically it gives you the what's the unit length of this screen is. And the width of this white block is 2 and the height is 1. So if you click your mouse and you can draw any curve, it doesn't have to be closed path, it doesn't be anything. Then once you finish, once you release your mouse button, it calculates the length of the line curve you draw in the screen. So way it calculates the length is not by measuring the pixel or anything. It has a formula called Cauchy-Crofton formula, and it simply calculates the length by taking the number of intersections, and the why the number of intersection gives the length is because of the theory behind the integration, double integration actually. So that's one. That's the project 5. I'm not saying this is the project 5. This is the prototype of the project. So I have 7. And so project 8 and 9. So I don't have prototype for project 8, but and also I want to change the title a little bit. So it's basically about Maxwell equation, and you will learn probably from next week about the integration and the vector fields. And there is a Maxwell equation. Actually, it's a partial equation, partial derivative equation. But anyway, that explains how the magnetic field and electric field are spread around the space. And the project 8 is how you could visualize this Maxwell equation. What I mean by visualizing equation is that you have to find a way so that people can see whatever you made to help their understanding of the Maxwell equation. So you have to devise your model, or devise your way to achieve that goal. So the last one is something related to this. So this is something that I made on my own purpose. So I was actually thinking about designing a class that teaches through the game making how the mathematics or theory of mathematics are applied. So this is one of the game that I made here, and it's a very simple game. So you click the dots. So you see there's a 7 number. So you should click the 7 dots. Then once you click all the 7 dots, then it makes the convex hull, actually the polygon, surrounding it. And then once you finish it, not only it fills the polygon with the color, certain color, but also it calculates the area inside of the polygon. So this one, the white box, gives you the idea of how much is 1 by 1 square is. So it's basically 104. So I don't have a unit, but the area is 104. So if the unit is meter, but then it's 104 meters square, and so on. So basically, I made it as a game that two-person can compete. I think it's still player A, and I think it goes for 10 rounds. And what it says is 55 on the top. It means that you have to make a 7-gon whose area is 55, where your unit square is this small. So it's kind of somehow you have to think of how could you lay out your point so that you can fit in about 55 blocks of these much can fit in there. So it's not that hard. It's kind of hard if you don't have an idea that. And also, what happens after 10 rounds is that the player B starts the game, and then after player B finished another 10 rounds, then it calculates how much the difference between the goal and your actual area, and it sums up all the differences and then compares the differences between player A and player B and decide who won. So that's a very simple game. I don't know whether it's fun to play or not, but this is just a prototype that you can make, and you can learn about the basic idea of Green theorem, Stokes theorems, and divergence theorem. Not the divergence theorem, but anyway, the all lies on the same principle that governs the basic idea of how you can calculate the area of a polygon. So this is something that you might consider when you do this project, the last project. Okay, so I'm going to pass this paper around and with a pen, and so you have to write your name under the section that you want to be for your second project. And as I said, if you want to be, so sorry for the small area. So here you have to write your name, not tiny, but small, not too big. So, so write your name and don't write your colleague's name, your future member's name, unless he is here, because I don't want conflict, because you thought this person might want to be in your group, but they may not want to be in your group. So write the member's name and your name in the same places, and then circle them around so that I can know who to put in the same group. So if you just write your name without any connection with other name, then I'll randomly assign you to form another group. So your group can be around 4 to 6. Your group can have 4 to 6 members. And the last time for the first project, I think I made the group too small. Some groups are too small, so we had too many groups. So I want the entire number of groups to be around 10 or 12 this time, or less than 10 probably. So it's okay to have 5 or 6 members in your group. Starting from here. So is there any questions? Any questions about the project? Okay, no question? Okay. So, so today I'm going to explain about the neural network. We probably have time to explain the or walk through some of the uh, prototype code that I made before. So I already put the video a long time ago explaining about this project, about the neural network, and you can watch it on the video on the list that I put up in the Notion. But I will explain again, so that you can have a fundamental idea about what's going on here. Okay, so neural network. So what's going here is the following. Oh, maybe okay. So I'll explain and then okay. So I'll explain it later. So neural network is okay. So it's what's the goal? What's the goal here? Designing a model that predicts an outcome according to the given data set. So you're trying to do something to predict. So for example, like what you have done before is to capture and try to put the capture image to the ChatGPT. And what ChatGPT does is to predict. Okay, so now it has a very sophisticated model, so it can output the answer, the prediction in a word that human can understand. But the basic model for neural network predicts certain numbers or values. Okay, so and in order to predict, it needs some data set, database, or some resource, so that uh, they can uh, they can tune its model so that it outputs the right answers for the customers or users. Now, what do we need to make a neural network? So basically, we need two things. What we need is first model. So what is model? I'll explain later. So second, the the mechanism or algorithm, or I should say method of optimization. So what is the model here? So model is basically a function. So what does function do? So the word function really means that it's doing something, right? So it's doing something that is predicted to be so if you're thinking about the function as a vending machine, then vending machine is supposed to be worked in this certain way. So and then when you do something in a certain order, certain designated order, then it spits out your kind of liquid. So same thing for the function. Function just gives the output according to your input. So model is the function. So you're trying to make a function that predicts whatever you want to see, okay? But however, you can just randomly choose any function so that your model works the best for your purpose. So you cannot just say y equals to x equals to your model for any random purpose, right? So the thing is, you have to have a method of optimizing your model. So what do you optimize here? What can you change? For example, if you're dealing with a function whose coefficients are not chosen yet, not tuned yet, then your coefficient of your function is something that you have to optimize to get the better output. So here's the example, not the neural network example, the basic example of these two schemes. That you have model and you have method of optimization to find out what you want. So, for example, the very basic example is you have 2 points. The goal is, okay, so if your data is just consists of 2 points on XY plane, then what you want, and suppose that this is the input of your data, and this is the output of the data. Okay, so it's X and this is Y. So by experiment or whatever mean, you got these two data sets, X1, Y1, and X2, Y2. You want to see what would happen if you take another experiment of your input and what will be the output. So your best prediction is just take the line connecting these 2 points, and then whatever you do on top of this 2 data set is following this line. So for example, if you take a point right here, for example, the third point, then what you can predict is your output will be on the line here, right? So you can do the similar thing with so these 2 points actually not just prediction, it's just determine one line, right? So if you have just 2 points, there are only one line connecting these 2 points. But however, think about the case when you have multiple points like this, lots of points, not just 5, and this is your data set. So you want to predict what will be the next output if I input another value of x. So your best prediction is you must find a line so that it best matches to your data set so that you can predict your next output of your next input to be somewhere lying on this line, right? So that's your best prediction. Now, how the problem is now how you could find such line, because there's no line connecting all these points because there are more than 3 points. And what's the strategy to make sure this line is the best prediction? Now you have to optimize your variables coefficient. So for example, let's say you have y equals to mx plus b. That's slope and the y-intercept, b, m, and b. And m and b can be randomly chosen, but then it doesn't predict the data set at all. So you have to find the optimal number for m and b. So what will be the method? So first, how do we know? You have to decide how do we know that this line is optimized, which means that it best predicts the data set. What you need to do is find the error between your prediction and actual values. So there's a confusion of words sometimes, which one is actual, which one is real. So what I'm saying here is these data sets have an error. You have to imagine that these data sets have an error. Maybe error comes from the experimental errors or other means. But anyway, these numbers are simply not ideal numbers, that the data set is not ideal. Ideal numbers are actually one that lies on the line. So we say x1, y1 up to xn, yn. These are data sets, and yi here is the real value. Let's say let's call it here real value. So real means that it was the value that actually got here. And let's say my yi given by putting in xi into the optimized line as yi bar to distinguish yi is the actual value. You see the difference? You have to see the difference here. So xi, yi is something that you actually, so I don't want to use the word actually. So you really got by experiment, okay? But that doesn't mean that yi is the actual value. That is not ideal value. So ideal value is one that you get from the line equation, because your experiment could have an error in your measurement or in your experiment, so that this yi without bar is something that you get after get the ideal value y bar with some error. So I'm assuming that this yi is actually yi plus error, epsilon I. So this is error on i's experiment. And this is ideal value. Ideal, let's see. Ideal value that should have obtained if there were no error. And this is the real value. So in real life, you get this yi. But in ideal situation, without any errors, then you might get yi bar. So now, well, we have to deal with what we have, the yi without bar. So what we have to do is find the m and b, which gives the yi bar for every index I, which minimize this error epsilon I as much as possible. Okay, so the goal is to find m and b that minimize the errors as much as possible. So here's a question. There's no one error. So how do we decrease the error as much as possible for all the IFAX experiment? So there are many ways to do this. One way and easiest way, and for analysis purpose, is that you think about the square of these errors for all the data sets. So I'm gonna call it L here. So what we want to minimize is not just one error for specific experiment or specific data. We want to minimize the square sum of errors of all the experiment or all the data set. So what is the formula here? So so you should understand that we don't know what error is yet. We only know that error is the difference between the real values and actual values. So we have yi minus yi bar squared. So yi is already a constant value, already known here. But yi bar is what we have to determine through the slope and the y-intercept. So it's mxi plus b squared. And let's expand this a little bit. So we have I equals to 1 and yi squared and plus m squared I from 1 to xi squared and plus nb squared and then minus 2m yi xi I from 1 to n. So basically it's the square quadratic function, so it's not hard to expand here. So we have 2b I from 1 and yi, just yi here. Then what do we have? Minus 2mb xi from 1 to n. Okay. So we're not still starting the neural network business. I'm trying to explain why we need model and how we need model and the method of optimization. And that actually relates to our discussion on the neural network. So we are dealing with actually the regression, linear regression here. So anyway, so focus on our objective for now. Our objective is to try to find the line that best predicts the data set. So by minimizing the square sum of error. So I want to minimize this value L. Okay? And how does L determine? So look at all the numbers here. As I said, I and yi is not variable. It's the constant. It's already given. So these are all constants. So so I'm gonna mark it different color. So this one, And where are the constants? So n is constant, and this one constant, this one constant, and this one. These are all constant. Okay, so I can replace it by some other symbol. Let's say a to f here. So it's a plus b times m squared. Well, let's leave it n here. So b squared minus 2mc plus 2 b minus 2e mb. Okay, so this a to e are all constant. Okay, so you cannot change it. What we can change, what we don't know yet, is m and b, the slope and y-intercept of the line. And then what it says about L is that what we want to minimize, the sum square of the error, is actually function of the slope and the y-intercept b. So it's actually two variable function, and it's a quadratic function. So it's a function of the L and B. So I want to find the minimum value of L, but actually I don't want the minimum value. What I want is when does this L becomes minimum? I want to find the point M and B, the value of M and B, make this function L as a two variable function gets minimum. That's my purpose. The goal is now find M0 and B0 that minimizes L. Okay. So there are many ways. There is actually ways to find the exact minimum point, but I'll introduce another method. So if you look at this quadratic equation of any type, then you can classify it into certain finitely many cases. And in this case, it always has a minimum. So you can imagine that this graph, well, we'll explain this later in the next time, so why it has always the minimum. So when your quadratic equation has a minimum, it always looks like this parabola whose concave, it's concave up here. So I want to find, this is somewhere in the xy plane, and there's a z coordinate here. So I want to find these points, m0, b0. So again, remember that we're not lying in xy z coordinate. I'm just giving the same idea of xy z space here. Although the point that I'm looking at is the mb coordinate. Now, where is it? How can I find this? The way you can find this point is that gradient descent. So what is the gradient? So gradient of a function is a vector whose coordinate is coming from partial differential. So let's say if your function is two variable function, then gradient is two-dimensional vector whose coordinates are fx and fy. So what does that mean? This means that it's the vector at xy where the value of function changes the fastest. So you have to move to the direction of gradient in order to change your value of function the fastest. So that's where actually matches to the perpendicular direction of your contour line. But anyway, so we'll actually need to discuss about this next time, but I'll just assume that this is a fact. And what we need to do to find this minimum point is that if you start off with a non-minimal point, then you have to find the shortest way, shortest path to get to the minimum point. So here is your starting point, let's say M and B. So you need to move your point M and B in the shortest path to the minimum point. Find the path that approaches to the minimum point. M0, B0. Okay. So how do you do that? Easy. Just you take the gradient of the two-variable function L. So that's actually in the slide. So I'll show you how the slide. I'll show you the slide here. So okay, this is it's the same thing, but I just changed the different symbols here. Instead of M and B, I used mu and rho, but the same idea. So what happens is, okay, so you start from one point, a random point, but I chose to be 2.9. I intentionally choose 2.9 here. But anyway, at that point, you compute your gradient as a two-dimensional vector because you already have your L, the function L, because everything is determined by the data set. This is simply a quadratic function. You know every coefficient. So you simply take the partial derivative of this quadratic function in terms of mu and rho, or M and B in our notes in the pad. Then you plug in this number 2.9, 2.9, where you're trying to get the gradient, then you get this gradient. So the number is rather big. It means that if you just use this vector to move your point, your 2.9, the meaning of 2.9 will disappear because the value is too big here. So you're not going to just move your point 2.9, 2.9 by this much coordinate, but you have to scale it. You have to rescale your gradient by small number, right? By taking a scalar product of small number to the gradient, so that you can move your 2.9, 2.9 a small bit, okay? Because in that, after all, what we need is the direction where we have to move our point, not how far we have to move. So you cannot get to the minimum point directly. You want to move it slowly, okay? So every time you multiply this gradient vector with a small number so that you can move your point smaller and small steps. So for example, your initial point is here. Initial point is here on the top, and so even though you're making a multiple of small number, since the gradient is very big, has a very big coordinate, so you can have a big stride from one point to the next point here. And then what happens to the next point? So once you get to the next point, this is your next point, 2.05 and 2.14 something, and you calculate the gradient again. So now the number gets a little bit smaller because now you're actually getting closer to the minimum point. So at this point, you have a gradient, but you still want to multiply the same amount of number you multiplied on the previous gradient to move your point in that direction. So you multiply the same amount of number to this gradient, 49 point something, 47, 3 point something, and then you move your second point to the third point. And then you keep doing this. So you'd see what's happening. So I already gave you the numbers here. So your 2.9, your initial point, is moved step by step towards these number, 0.9, 1.1 something. And then once you get to that point, your gradient gets smaller. The size of your gradient gets smaller and smaller. the reason why your gradient becomes smaller and smaller is that once you get to the minimum point, the gradient becomes zero vector. Because at the minimal point, imagine, thinking about the meaning of the gradient. I said gradient gives you the direction where you can change the value of function in the fastest way. Right, at the minimum, now there's no way, I mean, that's the bottom, that's the minimum point. Or you can have think about the maximum also same way, but at the minimum, you can move any direction to change your value, right? So it's minimum. So, and also your tangent plane to that function or graph of a function is flat. So your partial differentials are always zero. So once you get the minimum, you get zero gradient vector. So more and more you're closer to the minimum point, your gradient size of a gradient vector becomes smaller and smaller. So you're actually don't move that much until once you get closer and closer to minimum. So you have to, so in principle, it's impossible to get to the actual minimum by this method. But once you perform this step sufficiently many times, then you will have no effect of making your point move because your gradient vector becomes infinitesimally small. So you have to stop at a certain point. So there's you need to put some stop condition in when to stop. Anyway, once you stopped, that point is your minimal point where your sum of square of errors becomes smallest. So that's called a gradient descent. Okay. Now we are ready to talk about neural network. But before we talk about the neural network, I want to take any questions if you have any. So everyone understood about the gradient descent here. So remember this picture. Okay, so this is the only example we can visualize because gradient, I mean, you can only graph something on a three-dimensional space. And when we get to the neural network, the number of variables are way bigger than two, so it's impossible to visualize the gradient descent like this. So you have to remember this picture and then imagine that this same principle happens in the neural network when we use the gradient descent in the neural network. So let's go back to let's move to the neural network. I'll use the slide for a bit, and then if I need to, go back to the pen. So in our example, in our prototype project, I'm going to use the MNIST dataset. What is the MNIST dataset? It's the collection of images of handwritten digits, 0 to 9, and all the images are formatted the same, 28 by 28. So there are 60,000 images for training and how many was it? 10,000 10,000 for testing. So why did they separate the training and testing? So because these data sets are used for research purpose heavily, and then they wanted to not really now, because it's all old days. So once they train that once they have a model and train the data set, they need a same test set so that they can compare their model with the previous model or other person's model. So they need to fix they need to fix the test data set too. And these 60,000 training the images and 10,000 test images shouldn't be mixed, should not be mixed. Okay, so I'll explain the meaning of this, the deep theory of, not the deep theory, but the principle of the neural network. Okay, as I said, what we are trying to do in a neural network is simply find model, that's a two-step. Find the model and optimize the model. Just two things. So think about the modeling part. Find the model. How do we find the model? As I said, model is the function. It's a simple model is a function. Now, what function are we talking about? I want to predict the digits based on images. Okay, so what we know about function is, well, function in principle is assignment to one object to another object, but let me be precise. What we have done about the function is always a function is assignment of the list of values, for example, like a coordinate point to the list of values, right? Coordinate point, something like coordinate point. Now, we have a data set, MNIST data set, and it consists of images. And images consist of 28 by 28. How many is this? 784. Okay, so 784 integer numbers. By the way, the MNIST dataset images are always grayscale, so not in RGB. So you only need one value or one pixel to indicate the color, so from 0 to 255. So you have 784 integers range from 0 to 255, but you can imagine that this can be rescaled to a real number between 0 and 1 by dividing out by 255. So you can also think about this as the real number. Okay, so this is our inputs. This is something we want to predict. Okay, and predict to what? So once we have an image as a 284 list of number or list of 284 real numbers, what we want is, okay, so let me write this case, x1 to x784. What we want is, I want a function that predicts actual digits. Okay, so what is the actual digits? From 0 to 9. So I want this function. I want to have a function that best predicts this assignment. Well, that's simple. Okay, so there are many. So the one thing that I can do more is, okay, so I don't like this discrete set as my value of function. So what you can do is, there are many ways you can do. You can scale 0 to 9 to 0 to 1 by dividing by 9, so that if any value fall into the length between 0 to 1's ninths, then, or 1 ninth to 2 ninths, then you can decide which digits are which and so on. But okay, I want to make it a little bit simpler so that our arguments get more interesting. So instead of finding all the images or classifying all the images, let's say I want only 4, 0, and 1. Okay. So then the size of image is the same. So we still have 784 dimensional point as my input of our model, but my output is now 0 or 1. So I just want the number between 0 and 1. So I can imagine that my codomain of the model is 0 to 1. Okay, even though the actual value, the actual data labels the image either by 0 or 1, my model as the real value function could have a value range from 0 to 1. So I can just say my function that I want to find is a function of this. So let me be a little bit precise in my notation. So image is these points. So these points are member of 784 dimensional space, and my function is mapping every point in 784 dimensional space to the interval from 0 to 1. So I want to find this function that best predicts. So how do you know? How do you know the prediction is that? How do you interpret your prediction of your function? So, for example, if you let's say input any random image, or let's say the same format of your MNIST data set. Once you take the image and you put that into your model function f here, and you get some output in between 0 and 1. So if that is less than 0.5 or equal to, but doesn't matter because almost none of them, it's really rare that you have equality happens. So anyway, if your value of function is less than 0.5, then you label it or you predict that image is 0. And if it's bigger than 0.5, then you predict that the image is 1. Okay? So that's how you can predict your image as a digit. So the question is, how can we find this function? So there are two questions. What is the shape? What is the formula of this function? And the second question is, how can we optimize this function? So first question, what is formula of f? So there are no answers to this in principle. Whatever works is the answer. Okay? So our purpose is to get the best prediction, not the best function. There's no way, there's no term best function anyway. So the question should be something like, what is the formula? What is the simplest formula? But simplest means nothing, right? Simplest formula of f that works. Works means that it can predict the image properly. Okay. So what's the simplest formula can you think of? Well, we have dealt with the many basic functions like exponential, logarithm, sine, cosine, but overall, the simplest ones are polynomials. And among the polynomials, the simplest polynomials are the linear ones, which has the highest degree 1. So the polynomial of degree 1, that is, i.e., linear function, can work. Well, that's what people found out. It works. Okay? And it's very simple. It's simple enough that you can just simply put that into a matrix multiplication. Now, what will be the formula in this case? Okay, so you have 784 variables to input into your model. That means if you want to make a linear equations with this 784 input variable, then you need 784 coefficients. So your function will look like w1, x1, w2, x2, up to w784, x 784. And also, in order to be a general linear function, you need a constant term. No more. So in principle, you need 785 variable or coefficient or constant in order to fix your function f. So that's not it, because we don't know what the coefficient W and B is. The next step is we need to optimize this W and B. Okay. So now here's where your picture, the famous picture comes. So here you have x1, x2, and up to x78. So it's called a neuron. So neuron is not really a biological neuron. Neuron is a number depicted as something similar to the nucleus of a neuron. Maybe I'm wrong, but anyway. So, and then it's connected to some node. So the arrow sometimes. Here, each arrow or node is a 784. So it's assigned by this coefficient W. Okay, and then where does it point to? So another neuron. So let's call it Y here. Now, so this is Y. So by the way, so we have another not a neuron here. So it's not really a neuron, but it's depicted as a neuron. So neurons are the input values here, and the W are the node here, and B is the role of B is equivalent to the role of W, but in the neural network, usually depicted as another shape of neuron here. But anyway, so that's your Y. So this is Y. Now, the question is, as I said, I want the function to have a value in between 0 and 1, because if that's if when the function value lies in between 0 and 1, I can predict the image digits by this simple principle, right? But however, when you use these linear functions, then you don't have any guarantee that this value lies in between 0 and 1, right? You can have, lots of different x values, right? So you can't control it. You can't control the range of your y. Therefore, you need use another function. So technically, it's activation function. So I'm going to introduce another function sigma and then turn that into another neuron here. And what is sigma? Sigma is 1 plus exponential, should 1 and exponential minus 1. Let me think. Y is infinite, then it's 1 here. Y is infinite, then it's 0, and y is minus infinite, then it's 0. So what I want is transform the y values into z values, where z value always lies between 0 and 1. So here's the graph of this function. This function is called sigmoid function. So that reminds you some words, reminds you some presentation you heard. Okay, so then your final neuron that always lies in between 0 and 1. Well, in principle, it cannot be 0 or 1, but that's fine, because that's not what we're looking for. That's not what we are looking for. We only look for whether the value lies below 0.5 or above 0.5. Okay, so that's our model. Okay, so what is model here? So the entire model is, let's see, well, the entire model is this, not just f. It's the f composite with this activation function, sigmoid function. Okay. Now, what's the next step? Second step, optimize. First, this model doesn't work because you don't know what W, you don't know what B is. Random choosing W and B doesn't work. We have to fine-tune these values. How do we do that? We need to use gradient descent. Now, in order to find gradient descent, what was required? In our linear regression, we need something to minimize. We need to minimize the error, right? So here we also need something we need to minimize. What is something here? That is called a loss function. I'm going to call a loss function. And what does it measure? It measures the difference of the answer to our prediction. So when you input your image into the model, you get an output as a Z neuron here, Z neuron. But that image already has a label. Okay, it already has a label. So all the images are comes with the answer, the labels. Let's say you input 0. If you have here, if you have this image 0, then it has a label 0 as a number. Okay, and 1 here has a label 1. So you want to compare this label as a number with a prediction as a number and find the difference. You want to decrease the difference between answer and prediction. So the loss function, or let's just write it as L here, is what? You first take the composition of F and sigma, and let's say you input your image here. Image is just the vector x here. And then you take the label, so this is the label of the image x here. And okay, so if I just take the difference, it could be negative or positive. So that's not good, because negative or positive doesn't have really meaning. The important thing is the distance, how far your prediction is from the answer, right? So what we really need is the absolute value of these two differences and the difference of these two numbers. But when you take the absolute value, the problem is, think about this function, absolute value of x. It's not differentiable at 0. So it has a sharp corner. So we usually don't use this absolute value function, usually not using it in our optimization. So we take the square, okay? So y squared, y quadrant, y force, the power of force. Well, square is the simplest way you can get the positive number. So your L, the loss, or so why is it loss? So I think it comes from some physics backgrounds. When you think about the entropy, there's a loss of entropy. I think the idea comes from there. So loss is something that, you know, when you predict something correctly, but you lose your control, or somehow you lost your accuracy, and that's why it's called loss. So what you want is you want to minimize your loss. Okay, so the goal is to minimize the loss. So now it comes the gradient descent. Now, before you apply the gradient descent, let's think about this loss not as a value, but as a function. Okay, then that's really important. What are the variables of this loss function? What are the variables of loss function? So let's write this way. When I take loss, okay, so I take y, but is y a variable? Is y a variable or not? Can I change y? No. Y is given. It's a data set. So y is not a variable. It's a constant. And let's think about sigmoid. Okay, so here is 1 plus exponential minus f and 1. And okay, so is x a variable? No, x is just given value. It's also the data set. It's the one in the data set. It's a constant. Okay, where is the variable? Is L always constant? What can I change? What is the parameter here? So actually we missed this variable here in our notation of function. So we missed all these variables, to W1 to W784 and B. These are all missing. So what actually is here, it's 1 over 1 plus exponential of minus of sum of Wi xi, where I1 to 784 plus b squared. Okay, that's our formula. That's our actual formula. And we collect all the variables, wi and b. These are the variables that we need to determine. These are something we can change. So our loss function is actually the function of w and b. So here I abbreviated all the w's into w vector. Okay, so this function is 785 variable function. Okay, so it's a big function. I want to use the gradient descent. So how do you use it? You simply take the gradient. Okay, so I want to find the gradient of L. So you can consider that as a vector, or since this L is the real valued function, what did we say about the differential of a real valued function? It's column vector, right? It's 784 to 1 function. So therefore, it has 784 rows and 1 column. Okay? So you can consider it as DL. So it's 784 by 1 matrix. And this one is 784 dimensional vector. But they're the same thing because the coordinates are the same given by the partial differentials. So these are, let's say, W1, a partial differential by W1 and partial differential by W8, 784 and partial differential by B. Well, actually, it's not 784, it's actually 5, right? So it should be 5. Okay. So now, how could you take the partial differential of this much variable? And you know, this might not be that complicated, but if you have lots of layers, which I will introduce later, but then taking partial differential of this complicated function is way complicated. It takes too much time. So that's where you use chain rule. That's where you use the chain rule. So think about L as a composite of several functions. So what is it? Let's see. First, you have function f. So now the function f is not a function of x. It's a function of w and b. And then you take the composite with sigma. And then you take the composite with L, where L is let's see, Lz is y minus z squared. Okay, so y is constant. So you assume that x and y's are fixed here. Okay, so we don't change it right now. So once you take composition of these three functions, that's where you get L as a function of w and b. Now let's use chain rule on here. So if you want to take the partial differential of L, then it is the multiple or just product of differential of L, differential of W, sigma, and differential of F. dl times d sigma times df. Okay. So what is dl? So dl is just single variable function, right? Just one variable function. So dl is just L prime and 2 times y minus z. So it's 2 times y minus z. And then what is d sigma? As I said, sigma is sending y to z, where 1 plus x minus y, 1. So it's also one variable function. It's a single variable function. So d sigma is sigma prime y, and it's 1 plus x minus y squared, and take the differential denominator minus x minus y. So the interesting part is you don't need to compute the exponential again, because you already compute the exponential when you find the z. So this can be interpreted as 1 over 1 plus x minus y times 1 minus 1 plus x minus y, 1. And what is this part? It's z, or you can call it sigma y. And what is this part? It's 1 minus z. Okay, so d sigma is simply z times 1 minus z. And now what is df? So now df is really simple, because f is a linear function. df is x1, x784, 1. Why? Well, again, let's see. F W1 to W84B is x1 W1 plus x784 W784 plus B. You simply take the partial differentials on each W and B. What you get is the coefficient of W and the coefficient of B. So that's x1 to x784, and the coefficient of B is just 1. So you get this df. So here. Yes. So what is this? That's your partial differential. That's your gradient. So all you need to do is to move your W and B to the direction of this vector. You can see that this is just 785 dimensional vector, because it's all constant, the real number multiplied to 785 dimensional vector. So when you think about each coordinate, each variables W here, so each W I are moved to Wi plus. So actually you have to decrease it, so you don't have to, you shouldn't add to the gradient direction. You have to subtract to the direction of gradient. So subtract by certain amount, small number h, times the component of this vector is 2 times y minus z times z times 1 minus z times w, no, xi. So you simply change your previous w to the new w by subtracting this much with the scaling factor. So it's a learning, so this one is called a learning rate. So if you take the h too small, tiny, then you changing your WRI small so that you need lots of training, lots of iteration in order to get actual difference uh, of WI. But if your learning rate is too big, as I showed you before, then you don't want you end up being in a place where you don't want to be, or ping pong somewhere far away from the minimum values. So you must get the learning rate appropriately small, not too small, not too big. And what happens to the B? So that's for the W. And B is always at every step when you take the gradient step, minus H times this much. And that's it. Once you get sufficiently many iterations for moving your W and B in each with these directions, then you end up having a model that is optimized for your data set. Now, here's the tricky part. So what is the data set we are using here? So far, I just fixed my X and Y. So when I fix my X and Y, I'm dealing with only one image. Okay. So I can train with the one images over and over so that my model is best fit with this certain specific one image. But what our goal is to make a model, general model, so that it works for any type of handwritten digit image. So I cannot stick with one image. I have to feed this model many images as possible, right? So there are many ways to, um, many ways to train this model. So one way is what I already put it in the slide is that. So here is a separate issue here. How to train. So train your model. So train means optimize. So naive way is use one image at each gradient descent. So as I said, each time you optimize, you need one gradient step. So this method is something like you take one image and you find the gradient direction so that you can optimize your model with this image and move your variable to that direction a small bit. And then you discard that image and take another image and then take the gradient and then move your parameters a little bit more. Okay, so once you've done that, okay, so you've used the first image and then you use the second image. When you train your second image, it may not go to the same direction that for your first image. However, if your image data sets are consistent, for example, if you train your image as 0 at the first training or first gradient step, and then you train your image, the same image but labeled completely different, then you have, going in the opposite direction and being things that gets weird. But if your images or if your data sets are consistent, let's say first image is 0 and second image is also 0 but similar, but not same. I'm not saying it's the same thing, but it's similar, then your gradient descent will point to similar direction to your first training. So you get the actual minimum loss function, minimize the loss function. So once you get this all image data once, then you probably, guessing that your model can predict your entire image correctly than before. That's a one naive way. And if you don't satisfy with the result, then you can do it again, like iterate all over again, like going through all the images again. And second way, that's more popular way and more desired, is that don't try to train one images at a time. You train your image, several images at the same time. So it's batch, it's using batch. So if you find any video on the neural network, it explains really nicely, but I'll just explain shortly here. So suppose that you have, let's say, 6,000 images. So what you're doing is you're randomly grouping your images into hundreds images. Okay, so there are 600 groups in that case. So, and then what happens is you take these 100 images and take the average. So how do you take the average? Because you have 100 images, so it means that you have 100 vectors, x1 to x100. So each vector is 784 dimensional vector, but there is a coordinate for each vector, and you take the average of all these 100 coordinates for every places. So you get the average. So you get the average. And then use this as your input, and use this as your model, x place of x. And how about the output? How about the label? So each image are labeled by so y1 to y100. You also average out those. So you also average out these numbers and you get y. So and then use these to train your model. So in some sense, it somehow blurs out your images, but and also the effect of one image are the effect on the training of your model for one image is down by 100 compared to the training images by images. But let's suppose that you've done this 600 times, so you can sweep all the images of 60,000. Then you're not stopped there. You do it 100 more times. So it's called epoch. So when you sweep all the data set by batch size using the batch size, it's called one epoch. So if you do the 100 epoch, then you basically, in principle, sweeping all the images once. So you get equivalent, in some sense, equivalent result equivalent to taking one image at a time. And also, you don't have to stop at 100 epoch. You can use 1,000 epochs and so on. So you get iterating all the time. So when you get the next epoch, then you have to re-randomize your batches and then do it all over again. So that's one way you can, another way you can do it. Okay, so I'll stop here and then take any questions if you have any, because I've been saying a lot. So I want you to get the understanding. Yes.
Y has always been
Y is always the same
in the loss function.
in the loss function. Yes. It always is a constant. This Y. This Y is constant.
Not necessarily.
Which one? This one? Here? What Which one? Oh. Which part? Here? Here? Yes, it's a constant. It's a label of your image. So it gets given with the image. Okay, so, well, if you heard about the forward propagation and backward propagation, so forward propagation is finding that for prediction or whatever reason. So forward is going in this direction. When you input the image with the label, then, oh, by the way, so, okay, so there's a misunderstanding probably because I used the same same notation here. Okay, so this y is different from this y. Okay. So yeah, yeah. If I change it, then I change everything. So yeah, just look at the arrow here. This y is not same y as I put it here. So anyway, forward propagation is the forward. The word forward comes from the direction of calculation. So you get this input, and then you keep move forward to this direction, and then get the output. And backward propagation is actually when you optimize your W, so by chain rule and gradient descent. So you're going backward. So here we only have one layer to optimize, which is here. This is only layer that we need to optimize. So, but however, you can have several layers. That means you optimize this layer and then you optimize the next layer, so it actually goes backward. So that's why it's called the backward propagation. So when you train your model, you need the forward propagation and backward propagation, iterates for many times and goes until you get the satisfactory result. So any other questions? So where is the sheets? Where is the name sheets? Has anyone not written your name yet? Okay, so can you move? Can you pass the paper to back? The way back over there. Did you write your name? Okay. Right. So we have less than 15 minutes. So I'll just show you the code. Not sure whether I can show you the results. I'll just show you the result code, and then not this one. Let's see. Okay, let's see. Code is here. So the Google Colab, I think they already have a preloaded data set. So it's very fast to load the MNIST data set. But when you're working in your local computer, it takes lots of time, and also takes up some memory space. Okay, so I'll explain the code. So these are the packages that I need. Basically, I just need MNIST for loading the image, and if you could download somewhere else, then you can use it. Then we don't need the support. Anyway, so MNIST dataset consists of 28 by 28 image, but I resized to 10 by 10 just to make just to make this thing going fast. But maybe I can ignore this to check whether it works. So anyway, here's our sigmoid function. I already defined it here. And I made a class called CNN. It's not really CNN, it's convolution. It's not a convolution. I'll change it to name NN. But anyway, so if you can make a CNN convolutionary neural network. So far I didn't explain the convolutionary neural network because there's no convolution going on. But if you want to analyze a complicated picture like a car, a cat, then you probably need a convolution neural network. So what happens is first when you create your model, you initialize your rate or size. If it's not inputted, then uses the constant defined in here. And weight and bias, weight is the W and bias is B, is randomly assigned. And then you update. So it's actually the forward propagation. Update is the forward propagation and predict is the backward propagation. So update is when you take an image and you compute your, sorry. So it's predict is a forward propagation. So I think I changed this code after I wrote this a long time ago, and so I was confused. So predict is a forward propagation. Basically, I put the image, my image is an input, and then put that image into what is it? The linear function. So the NP dot means that I take a inner product between two vectors. The one vector is the vector of W, and the other is vector of image, which is X, and then add the bias. That's the linear equation of the image, and then put it into sigmoid. So that's an activation function. So although I put that as a y, but it's actually z in our note, and return 0 if y is less than 0.5, at 1 otherwise. And that is actually in order to just predict, test the model, test the accuracy. So what actually is done is update part. So update part computes the same thing. So it's the same, basically the same thing going on in the prediction part. But once you get this y, here's the thing. So you have this y minus level because I think it's somewhere. So I think the same thing. Oh, maybe I forgot. No, maybe I think I forgot to put the negative parts here. So since I have, oh yes. So yeah, I forgot the negative sign. So here, if my L, the capital L is this, then DL, L prime is minus of this, right? So what I should have is Z minus Y, not Y minus Z. So anyway, so this is the DL part, and this is the D sigma part, and this is the image part. So basically, I only have X1 to X74 for my update of W. So that's my DW. This is how much I should change my each W line. So you can see that this is not a constant number. It's a vector. It's an array. And DB is just a number. And I'm updating the weight vector of this class by this much by multiplying the rate, learning rate, and then same for the bias number. And I do it one by one. So I can feed my image and the label, but I can also use a batch size here by taking average of group of images. So here's the resizing function. So what happens is I first take the image, training and testing image, and then I sorted out the images only for 0 and 1. That's what I'm doing here. And then I first check, I first create the neural network, and then when you first create neural network, all the variables are randomly assigned, so there's no prediction going on. But actually, but I did anyway. So I predicted all the test images and calculate the success rate, and I did the training, train the image one by one, and then after I finished it, so this is the training part. This two line is the training part. And then after I done this, I also do the same thing, calculating the accurate rate, then compare these two results. I'll see how it looks. Oh, it's done already. So here's the success rate before the training, which is 53%. Basically, it's not done yet. Okay, so it was a previous result. So it's doing the work. So before the training, it's somewhere between 50%. So basically no prediction going on. But once it's downloading actually. So once it's fully trained, then the success rate goes up to like 99% because it's easy sets of image. It's just 0 and 1. If you want to have a model that predicts all the digits from 0 to 9, then you cannot use one value, one neuron. You cannot use just one neuron. You need to have 10 neurons to classify your image. Okay, so here is the result. So you get 53% before training, but 99.9% after training. So one that it failed to predict correctly is this image. So it's a rescaled image from 2820 to 10 by 10. So it's a little bit blur, but it's a 0 with the dot here. So that's why I think it's failed to predict. So anyway, if you want to classify, use other data set, which has more than two labels, more than two types of labels, then what you want to do is make up your model like this. So here you have same inputs, x1 to xn. So it doesn't matter. I mean, n depends on the size of your image data. So what you want is basically something going on here. Okay, is output y1 to ym. So the m is a lot less than n. So m is the number of classification, and these yi's are also assumed to be normalized to the number between 0 and 1. So once you have this model, so now your function model as a function is function from Rn to Rm, right? So you can design your model to be a linear function or composite of linear functions. But now, how do you predict with this model? How do you predict your image? So each y1 to ym is number between 0 and 1. You pick the largest number. Okay, you pick the largest number and consider that as your prediction. So for example, you have number 0 image. So among these 10 images, you can label this image by 1, 0, 0 to 0. So it's a 10-dimensional vector. One at the first position, because 0 is the first number in the 10 numbers. Okay, so it's called a one-hot vector. So because there's only one vector, one number, and rest of the coordinates are 0, one-hot vector. So, and also you can do the same thing for 1 images and 2 images. So all the labels are coded into one-hot vector, and then you can compare the difference between this one-hot vector the answer sheet with the result y1 to y10. So how? You take the negative of these two and then take the square sum of each coordinate. So you want to minimize the square sum. You want your prediction as a 10-dimensional vector as close to one half vector like this. So you don't want something like 0.5, 0.9, 0.9, something like that. We don't want this. We don't want this kind of prediction because it's giving you the something closer to the answer sheet here. So now you have one more step to composite, but everything is the same thing. Once you have all the functions as a loss function composite of several functions, then all you need to do is take the gradient descent from the outside function to the inside function and so on. So once you have this, everything is getting simple. The filtering is just the technical part, not the core idea of our neural network. And you can do more, and you can also implement other types of neural network, or maybe not the neural network itself. You can try another things because all the optimization these days are related somehow grounded on this chain rule and gradient descent. Maybe not the gradient descent all the time, but anyway, the chain rule is always there. So if you try to do this project as your second project, then you want to implement mathematical idea and into your code, and try not to copy or use others outside resource as possible. So it's okay to take some outside library to make a GUI, or file input and output, or making a data set, but inner working of your model or neural network should be implemented on their own. Okay, so we're almost time, and oh, by the way, I have an important announcement. We don't have class on Friday, this Friday, so I have a doctor's appointment on Friday. I have to go somewhere else, so we don't have a class on Friday. I'll try to post the video to make up that class. So good. So if you have someone friends, I'll put the announcement on the LMS. But if you have a friend who did not come today, then tell them that there's no class on Friday, this Friday. So see you next week.